This video is going to focus on how to write and balance an example decomposition reaction. I'll also try to go ahead and add up all the masses for each part of the reaction with regard to the elements and the compound packages and use that to make a prediction using unimultipliers in the end. Now, in order to do decomposition reactions, you guys have to be aware in the directions or on a handout that the decomposition compounds either end with a carbonate, a hydroxide, a chlorate, oxide, or as an acid. And we have to kind of give you guys a heads up on what the products are going to be. So you will have a list of these, or it'll be provided in the directions on a question. So I'm going to first go and start writing the equation in formula for the formula version for potassium carbonate. If you look on your ionic handout, or excuse me, on your polyatomic handout, carbonate is a CO3 package of nonmetals. Now, since this is ionic, I'm going to go ahead and do the charge balancing. Carbonate has an overall charge of -2. Potassium's a +1 on the periodic table. These are not charge balanced. In order to charge balance them, I need to put a 2 on the subscript for potassium. Now that I have 2 potassium, it's a +2 overall to balance out the -2 carbonate polyatomic package. Now, if this was to decompose, the best way you guys can figure out how it decomposes is by looking at the little cheat sheet we have to provide for you. So this is a carbonate. It has the carbonate polyatomics. We need to follow the directions on carbonate over here on the top right. These bullet points are these carbonates, hydroxides, chlorates, oxides, and acids. This was copy and pasted from an in-class worksheet you guys have in your possession. So a carbonate usually produces carbon dioxide gas, which is a gas that puts out a flame on a splint test. I've done the splint tests off and on throughout the year, and you guys should be aware of the possible outcomes for the type of gas if a flame goes out, burns brighter, or actually ignites the gas. But in this case, it's carbon dioxide, but it also ends up leaving a metal combined with oxygen to make a metal oxide. So I'll go ahead and write out the CO2 gas, and then it leaves a metal oxide. The only metal we have is potassium. Now, because potassium oxide is ionic, I have to charge balance them. Carbon dioxide, I do not have to charge balance. Potassium's charge again is +1. Oxygen is a -2. They are not charge balanced. The only way to do that is to make potassium have 2 potassium for the whole package in this whole compound. Now that I have the compounds charge balance, I need to make sure I have all the mass accounted for. You guys can use the T-chart method if you want to try it. I'm going to try to use it on this video. So I'm going to do the reactant side, the left, and I'm going to do the product side on the right. I'm going to start off with the carbon atoms. In the beginning reactants, I have 1 carbon atom currently. The products, I have 1 carbon atom also. I'm going to move on and do the oxygens on the reactant side. There's 3 oxygens. On the product side, though, you have to total up all the oxygens. So there's 2 oxygens for CO2, and there's 1 oxygen for the potassium oxide. So I've also got 3 oxygen on the product side as well. Finally, the potassium. I have 2 potassium on the reactant side, and I've got 2 potassium on the product side. So it's already mass balanced. We do not have to put any coefficients in the front of any of these packages or compounds. So use this technique on any of the reactions we do, but when it comes to decomposition, you need to know the outcomes from the teacher notes here or on your handout in the directions to be successful at doing this. I will do sodium chlorate decomposing down below. Sodium chlorate is an ionic compound because it's a metal with a non-metal package. Chlorate is a polyatomic ion, so you have to look that up on your polyatomic sheet. Chlorate is ClO3. And chlorate has an overall charge of -1, +1 for the sodium. So it is charge balanced at this point. However, if we run it through decomposition, we have to read what chlorates typically break down into. If you look in the top right teacher notes section here, chlorates usually produce a metal chloride and oxygen gas. And when you have oxygen gas for the splint test, it'll either reignite the flame or it'll make the flame burn brighter. So I'm going to go ahead and do the metal oxide, or excuse me, metal chloride. The charge on a chlorine is -1. Charge on a sodium is negative or +1. They're canceled out and balanced out from a charge point of view at this point. The chlorate said that it also breaks down into oxygen gas, so I need to put oxygen. Remember that when you have oxygen and other elements such as nitrogen, hydrogen, fluorine, chlorine, bromine, and iodine, they're going to be diatomic when they're all by themselves. So you have to put a 2 on there. Now that we have all the products written out, all the compounds charge balanced for ionics, now we need to mass balance it. Once again, I'm going to go ahead and try to use the T-chart method to keep track of everything. I'm going to go ahead and start with the oxygens this time, just because on the reactant side, there's 3 oxygens that are going to dominate the left-hand side here. On the product side, I have 2 oxygens currently. And then I'm going to go down the list. I'm going to do my chlorines. I have 1 chlorine on the left on the reactant side. And then I have 1 chlorine currently on the product side. And then the only thing that's left is the sodium. And I currently have 1 sodium. On the product side, I currently have 1 sodium. Now, in order to take care of the oxygens being out of balance, you need to think about a common multiple that they can both go into. And most people would say 3 and 2 can easily make 6. So I'm going to put times 2. And this might be my new coefficient I'm going to apply. And then on the product side, I'm going to go times 3. And the 3 might be my new coefficient at this point too. So if I apply a 2 to the coefficient on the reactant side, that fixes me having 6 oxygens on the left now. And if I take the 3 and put it with the only pair of oxygens here, I have 6 oxygen here. So by changing those coefficients, I now have 6 oxygens on both sides, and that's mass balanced. Now, the only thing to do now is to look to see what that decision has changed or modified. By putting the 2 out front of the sodium chlorate, I've now changed how many chlorine I have and how many sodium I have. So this 2 that I came up with for the oxygen is applied now to the chlorine and the sodium. Now, in order to fix that on the product side, luckily sodium and chlorine is by itself. So any coefficient I put out front can help fix the damage I've just done. So in order to get the chlorines and the sodiums balanced out, I'm going to put a 2 in front of the sodium chloride. And now I have 2 sodiums on the reactant side, 2 sodiums on the product side, 2 chlorine on the product side, or excuse me, the reactant side, and 2 chlorine on the product side. Now it's mass balanced. Now I can use this equation to make mathematical predictions using unit multipliers. So I have a really basic unit multiplier we're going to do here, but first we have to add up all the masses of the compounds and of the elements. Remember, when we add up the masses, we're going to leave the coefficients out of the calculations and put it outside the parentheses. So I'm just going to add up the sodium, the chlorine, and the 3 oxygen, because I want to know the weight or the mass of one package of this compound. If you look on your periodic table, you should see that sodium is 24.31 grams. You should see that chlorine is 35.45 grams. But now there's 3 oxygen. When there's a subscript 3, go ahead and multiply it now because it's part of the compound. So you should be able to take 3 times 16 grams from the periodic table, and you need to total that up. If you total that up and my calculations are correct, you should have approximately 107.76 grams of sodium chlorate in the reaction. But we also need to put the 2 out front for the coefficient and take it times 2. So we're going to use this whole package times 2 in our unit multiplier as needed. Now if we come down here and do the products the same way, sodium again was 24.31 grams. There's only 1 for now. When you look at the compound alone, I do not want to include the 2 for the coefficient. I want to know that you guys know the mass of the compound alone, a single compound. I've got 1 chlorine, so I'm going to put 35.45 on here again and total that up. If my calculations are correct, you should have something like 59.76 grams of sodium chloride. And again, we're going to take this times 2, but not until we use it in a unit multiplier. And now I'm going to add up the oxygen over here. Again, leave the coefficient out for now. For just a package of oxygen, which is diatomic, we're going to take 16 grams times 2 since it's diatomic. Which is 32 grams of oxygen. But remember, there's a coefficient in front, so we need to put a 3 on front. So to do your unit multipliers, we can now use any of these packages to build a ratio. Just like any unit multiplier you would do normally with known ratios. So an example I made up, just imagine that you have 180 grams of the starting reactant, sodium chlorate, but you want to find out how much gas you can make out of the 180 grams of sodium chlorate, how much gas of oxygen you might produce. In order to do that, I need to set up a unit multiplier where the denominator is taken from the reaction and cancels back the sodium chlorate we no longer want for units. So I'm going to use what I know about sodium chlorate from the reaction. I know that 1 package of sodium chlorate is 107.76 grams, but the recipe or the reaction calls for 2 servings of it. So I'm going to steal that and write 2 times 107.76 grams sodium chlorate. The grams sodium chlorate will cancel. But I need something from the reaction in the recipe to jump to the oxygen gas I want. If you remember, a diatomic package of gas, of oxygen gas, is 32 grams, but there's 3 servings of it according to the recipe or the equation. So now, only units that are left are grams of mass for oxygen, which gets me what I wanted to predict. If you multiply across the top, and then you multiply the bottom, I want to see 2 steps of simplification here. If you go across the top, you should see that you get approximately 17,280 grams of oxygen. Bring over the 2 times 107.76, and that should be approximately 215.52. And again, no units on the denominator because we just canceled them out. And now if you simplify this, you should have approximately 80.2 grams of oxygen produced, as long as my calculations are correct. But use this method on any of the reactions that we've given you guys. Any of the equations, you can add up all the masses of the element packages, the compound package, and set up a unit multiplier to make predictions.